So the topic sound, these are the learning objectives, like how sound can be produced. It can be produced by vibration. So whenever we want to produce a sound, what we do is we disturb the surface, and that surface cause a vibration of the air particle and produce a sound. And whenever sound is produced, sound is longitudinal in nature. What does it mean, longitudinal? If, for example, this is a cone of a loudspeaker, it is vibrating. So the direction of the energy transfer is towards the right hand side, and when we check the direction of the movement or vibration of the particles, that is also right and left. So the particles vibration, the vibration of the particle is same as the direction in which the sound travel. So what we call this, we call that as a longitudinal wave. So longitudinal wave is the one in which the particle vibrate parallel to direction of wave. So sound is a longitudinal because in sound the particle vibrate parallel to direction of the wave. And it create a region where the particles are very close to each other. So region where the particles are closer to each other, we call that as compression. We can represent by letter C. And the region where the particles are away apart and pressure is low, we call that as rarefaction. So sound is actually travel from one place to another in a series of compressions and rarefactions. So you can see if we sketch a graph or show a graph for variation of the pressure for a sound wave. So in a compression, the pressure is higher, whereas rarefaction, the pressure is lower. This is also like example, a tuning fork is vibrating. As we check the direction of energy transfer, like right, left. So energy transfer example towards right, towards left, up or down. So the particles are vibrating parallel to the direction of the wave. So as the particles are vibrating parallel to direction of the wave, we call that as longitudinal wave. So sound waves are longitudinal waves which are travel from one place to another in a series of compressions and rarefaction. So definition of compression is a region where the particles are close together and a high pressure, whereas rarefaction is a region where the particles are further apart and the pressure is low. Audible frequency. All the frequency, our ear is not sensible or able to detect all the frequency. There's a range for a normal human hearing. There's a range of frequency which our ear can detect, and that is from 20 hertz to 20,000 hertz. So we can only detect this frequency, like sound within this frequency. Like some students get confused with the frequency and the loudness. This 20,000 hertz, normally a common question or a doubt is there that it's this 20,000 hertz can cause a person deaf. No, it's not like this. 20,000 hertz is a vibration, it's not an amplitude. The thing which can make you deaf is the loudness of the sound. Even a frequency is 20,000 hertz, but it is not a loud sound, so it won't affect your hearing. 20,000 hertz, if a sound is having a frequency of a 20,000 hertz, that sound will be painful in what sense? Because there are a lot of vibrations on the eardrum, so it will be painful on the eardrum and it will be a sharp sound, but it's not like it can cause a deafness to a person. So this is a audible range, this is a frequency range which our ear can detect. The sound which is having a frequency less than 20 is called infrasound or infrasonic, and the sound which is having a frequency more than 20,000 is known as ultrasonic. So ultrasonic sound is refers to a sound which is having more than 20,000 vibration, and the infrasonic refers to a sound, but we cannot hear ultrasound or infrasound. We can only detect the audible range. Visible I just get because of light, but it is the audible range which our ear can detect. So sound need a material, sound need a medium to travel. Sound cannot travel through a vacuum. So simple bell jar experiment is there. What we are doing in this bell jar experiment, there's a bell inside a jar, and we connect a pump or a vacuum pump. When we switch on this vacuum pump, there are air particles. There is air present. But when we switch on this vacuum pump, as a result, what happened? The air is removed from this vacuum pump. So when this air is removed from the vacuum pump, the number of the air particle will decrease. As the number of the air particle decrease, eventually no air particles, a vacuum is created. So when vacuum is created, even though the hammer is striking this gong, but we will not hear any sound. So this experiment confirmed that sound cannot travel through vacuum. Sound require a medium to travel. To find the speed of the sound in air, we can perform a simple experiment. How to find the speed of a sound in air? So what we have a stopwatch, a starting pistol, a measuring tape, or throttle wheel can also be used. So there is a person at A and another observer at B with a stopwatch, and a person at A is having a starting pistol. When a person at A is having a starting pistol, when he fired the shell, so two things will happen. The light and the sound will produce at the same time. But because the light is super fast, light is traveling at a speed of 3 into 10 power 8 meter per second. So light is super fast. The moment when observer B, he will see the light, he will start the timer. But sound take time to travel. So once this he detect the sound, he will stop the timer. So basically that is the time taken by sound to travel from observer A to observer B. And we will measure using a measuring tape or a throttle wheel. We can measure a distance, and to get the speed is distance divided by time. So distance divided by time will give us speed of the sound in air. Is it clear, this experiment, that how a speed of sound can be air? We can measure this, measure the speed of sound in air, or calculate the speed of the sound in air experimental way. Then the speed of sound in different medium, you have to learn this value. In a solid, it is about 5,000. Not all the solid 5,000, but most, like within this range. In a liquid, it is about 1,400. Yet time will be too hard to record, Abdullah, that's right. But if they are far away from each other, then it will be easy. This experiment is having error, like the previous experiment which we are discussing was having errors. It won't be 100% accurate, but still this is a way to calculate. So this should not be like, this should be about 300 meter or more than 300 meter apart, might be 600 meter apart, so that the observer B will have more time to start the timer and then stop the timer when he sees the when he see the light or flash, he will start the timer. When he hear the bang, he will stop the timer. So for experimental accuracy, they should repeat the experiment. They can switch the position now, like observer A will be at a position of observer B and observer B at position of observer A. So they can switch between the position. What is the concept of echo? The term echo means reflection of the sound. So when the sound strike the surface and it bounce back, we call that as echo. So example, this is the source of the sound. and there is a reflecting surface which is at a distance d. So there is a source of a sound and a reflecting surface is there. Which is at a distance d. So what happens, the sound, when we produce a sound, sound will travel and then it return back. So what is the, because if we want to find the speed or we want to write a formula for speed, so speed is distance divided by time. So what is the total distance covered here? First the sound travel a distance d and then it bounce back to a distance d. So total distance traveled by the sound is 2d. And how much time it took to travel, that is a total time. So whenever there is an echo reflection, you will use the formula speed is twice the distance, and that distance is distance between the source and the observer, a source and the reflecting surface. It is in the case when there is a reflection. But in the previous experiment, why we simply use speed is equals to distance over time? Because in this case, when the sound travel, it travel from observer A to observer B. It's not like coming back after striking. That's why we only took the distance d. So whenever there's a reflection or echo, we'll use the formula speed is 2d divided by t. So this word example, like to estimate the width of the valley, a climber starts the stopwatch and he shouts, he hears an echo from the opposite side of the valley after 4 seconds. So we need the distance of this. So how we can work out the distance? Sometimes the speed of the sound in air is not given. So you can take any value, like you can take 330 meter per second or 340. So whenever there is an echo, the sound will travel and bounce back. So the formula speed is 2d divided by t. We need this distance, we need d. So speed is how much? 340. In this case, they took 2 multiplied by distance, and time for the echo was 4 seconds. So we simplify, this 2 will be multiplied, so distance will come out 680 meters. So that's a distance between the valley as the climber is finding the width of this valley. Is it clear? So this is always the case when the object, when the sound waves are reflected. Then what is the concept of the loudness? Loudness of a sound is refers to amplitude of the sound. This is actually like in the figure. This is not the how sound waves appear. This is just a representation, because as we already, this is a transverse wave, but sound waves are what? Sound waves are longitudinal, in which the particles vibrate parallel to the direction of the wave. But just to explain the idea, when we draw a waveform, this is just to represent. In actual, the sound waves are not like this. So when we draw the sound waves in terms of transverse, the loudness of a sound is refers to how much energy transferred by the sound, and that energy transferred by the sound depends on the amplitude or the height. So you can see the 2 sound waves are there, the waveform of 2 sound waves. So which is having a louder sound, A or B? So in this case, B is having a louder. Why? Because B is having a greater amplitude. So greater the amplitude of the sound, greater the loudness. And what happens when the loudness of a sound increases? So when the loudness of a sound increase, the size of compression will be smaller, or will decrease, and the size of rarefaction will increase. This is what happened in terms of compression and rarefaction. The size of the compression when the sound become louder. Like example, if I say these dotted lines are representing the sound waves. So this is a compression and then rarefaction. Then compression, rarefaction. Now, if we say the sound become louder, so what change we will see if the sound become louder in terms of compression and rarefaction? So the compression size decrease, like particle will be much closer, and the rarefaction size will increase, and the compression size again decreases and the rarefaction size increases. So this is sound wave 1 and this is sound wave 2. So in terms of compression and rarefaction, what we will observe, this is the thing which we'll observe, that in a if sound wave become louder, the size of the compression decreases, whereas size of the rarefaction increases. Because you can see this was the original size of compression, like in the wave 1, and this is the size of rarefaction. But in the second wave, the compression is much smaller and the rarefaction is much larger. Is it clear? The concept of loudness, which refers to amplitude or how much energy the sound wave transfer, and it is directly proportional to the amplitude. So when you are shouting, basically what does it mean when you shout? It means you are producing a sound with a higher amplitude or sound with a more energy. Then what is pitch of the sound? Pitch of the sound is refers to frequency. Pitch and frequency is having the same meaning. Frequency means number of vibration. So pitch also means number of vibration. If we draw a waveform, this is not actual sound wave. This is just a representation. So this is having a few vibrations and this is having more vibrations. So if the wave is having more vibration, it means it is high frequency. And few vibration, low frequency. Low frequency means that low pitch, because pitch and frequency is the same concept. And high frequency means high pitch or greater number of vibration per second. But this is just a representation in terms of wave, but actually how sound waves are there. So when the pitch increase, there will be more compressions and rarefactions. So number of the compressions and the rarefactions will also increase as the frequency increases. So if this was a case, like example, we are representing a compression. So this is like a compression, then rarefaction, then compression, then rarefaction. So if we say high pitch, what does it mean for a sound wave? It means there will be more compression and rarefaction. Like if this was having like one compression, rarefaction, compression, rarefaction, we want to draw or we want to mark for a high pitch. So what does it mean? There will be more compression, rarefaction in the region. So greater number of compression, rarefaction, or more vibration per second. So that means that it is having a higher pitch. So pitch is refers to the frequency. Is it clear, the concept of the pitch? Any doubt till this point? Then what are ultrasound? As we know, the sound with the audible range, audible frequency range, that's 20 to 20,000 or 20 to 20 kilohertz. But sound which are above this range are known as ultrasound. And ultrasound is having many uses. Like example, to examine the body, we can also use ultrasound. For cleaning a delicate material, like some parts, they are very, like parts in the machine, like even parts in the watch. If they want to clean that machinery, what they do, they immerse that part in a tank which is filled with a liquid, and they cause a vibration of very high powerful ultrasound, and that ultrasound will dislodge or remove the dirt or the grease. Like example, say this is a part of a machine we want to clean, and it is having a dirt at the top. So it is a delicate part. So if it is a delicate part, we are not able to clean it by using like a sandpaper. So what we can do, we can just put this object into a liquid, and we produce ultrasound. So when we produce ultrasound, this ultrasound will cause a vibration of these particles. The particles start to vibrate, and these particles of a dust, when they start to vibrate, they will come off from the surface, and the object will be clean. So this is one of the use of ultrasound. It can also be used in detecting the flaws in the metal. How it can be used to find the flaws in the metal? A liquid is not making a sound. Sound can travel through liquid as well. So we are producing a sound in the liquid, and that liquid transfer the sound to the, or vibration to the dust particle, which make them tip off from the surface. So ultrasound can also be used to identify the cracks. How it can be used? Like example, this is a source and a detector. So if there is a crack in the metal, the ultrasound strike and then bounce back. So we can identify the exact position where the crack is there in the metal surface. If there was no crack, then it will take the same time to return back. Like example, if there was no crack, it will only bounce back from the surface. But if there is a crack, it will relatively take shorter time to return from the source, and the detector will record the time interval between the wave travel and bounce back. And using this idea, we can identify the exact part of the machine which is having a crack. So this uses a principle of echo or reflection. Same ways, we can also use, the ships also use this ultrasound. Ultrasound means sound which is having a higher frequency than with audible, which is more than 20,000. So ships also use this pulse echo technique. So they send the wave, and then it strike back. So how much time it will take to return back? Using this idea, they can identify, as we know the formula, that speed is they can also identify the depth or any object which is there, or what is the distance between the seabed and the water surface. So we have the formula, speed is distance over time. But because the sound wave are traveling, the ultrasound can travel, or sound wave can travel through liquid, and same like ultrasound can also travel through liquid. So speed is distance over time. Here distance will be twice because going and coming back. So speed into time divided by 2 will be distance. The speed, we know that when the sound waves are traveling in liquid, the speed is about 1500 meter per second. Time it will take, like we record the time it will take to go and come back. So we'll have the speed, we have the time divided by 2. So we'll know the distance between the ship and the seabed. Is it clear? So the longer the time it takes to travel uh, to return back, it means the deeper the sea. Is it clear, this use of ultrasound? So some of the bats are also, like, not some of the bats, all the bats are using ultrasound to detect the distance between the objects. So you will find that the ear of the bat is much larger in size. What is the reason for that? Because when they produce ultrasound, it strike and they can detect a small change in the frequency, and they can identify the distance between the source, the distance between the source is a bat here and this is a object. So they pick up the reflection and identify the distance. Same thing, whales are also using this technique, producing the ultrasound. So they send the ultrasound and then it bounces back, so they can identify or recognize the distance between the reflecting surface. So these are the uses of ultrasound. So this topic was a short topic, and this was the last topic related to block 3, which is about waves. Any question related to the class today? The next session we will do the topic wise questions from sound. So I'll end the session and share this with you.